Hi there, this is the talk for the paper called Sharper Bonds on the Fourier Concentration of DNFs. This is joint work with Liang Tan, my advisor at Stanford. And really what this is about is how simple are DNFs? Now, I haven't told you what simple or what DNFs mean, so let me get on straight to that. First, what is simple? This is about Fourier concentration, which is one part of the title. But first, I need to tell you a few words about Boolean analysis. This is the study of Boolean functions, and in most areas of computer science, we would think of Boolean functions as functions from 0, 1 to the n to 0, 1. But it turns out that for Boolean analysis, it's often more convenient to think of them as functions from plus or minus 1 to the n to plus or minus 1. And in particular, we'll be interested in the way that we can represent such functions as multilinear polynomials. Let's take an example. Let's look at the function, at the majority function on 3 inputs. So it's just a function that takes in 3 input bits and returns the most frequent one. And we can represent it as a polynomial in this way, as a multilinear polynomial. And we'll be very interested in the coefficients of the monomials of this polynomial. So for this reason, let's, for any set S, which is a subset of the set 1 through n, we will denote f hat s to be the coefficient of the corresponding monomial. So for example, the monomial x1 has coefficient 1/2. So we'll write maj hat of the singleton set 1 to be 1/2. And similarly, the monomial x1, x2, x3 has coefficient -1/2. So we'll write maj hat of set 1, 2, 3 to be -1/2. And we call those coefficients of this multilinear polynomial Fourier coefficients because there's in some way a Fourier transform in disguise here. And the nice thing about those coefficients is that they reveal properties of f. So for example, if you've heard of the bias, the influence, or the sensitivity of a function, those properties all have nice expressions as a function of the Fourier coefficients of f. And one particular property that will be convenient for visualizing them is that the sum of the squares of those Fourier coefficients is always 1. So one way that we can represent them graphically is kind of as pieces of a unit square. So you think of it as f being an entire unit square that you share up, that you split up between the different coefficients. So for example, for each set S, we associate to it a square of side absolute value of f hat s, so that the area of this square is f hat s squared. And since all of those f hat s squared sum up to 1, this splits up the unit square in some way. Now, one way to define simplicity as based on the Fourier coefficients is to say that if few of the coefficients are non-zero, then f is simple, and we would call it sparse in this case. And graphically, this just means that the unit square is split into few squares. So for example, here we have 1, 2, 3, 4, 5, 6 squares. So we would say that the corresponding function is 6 sparse. And sparse functions are simple in the sense that they have nice properties. So for example, they are easy to learn from queries. But the issue is that most functions are in fact not sparse. So even functions that we consider to be pretty simple, very few of them are actually sparse. So to fix that issue, there's a slightly more sophisticated notion, which is Fourier concentration. And we will say that a function is Fourier concentrated if you can split it up into 2 parts. So if you can split up the Fourier coefficients of it in 2 parts, one of which has small total area, and the other of which is made of few squares. So for example, if the first part has area at most epsilon and the second part has at most m squares, then we say that f is epsilon concentrated on m coefficients. This is actually equivalent to being able to epsilon approximate this function by an m-sparse function under some notion of approximation. And I claim that this is one of the most successful notions of simplicity in Boolean analysis. The reason why is that it's both flexible enough to apply to many functions. Many functions are sparse for some quantity m and some quantity epsilon. And it's also strong enough to give nice properties. So we still have this property that you can learn it efficiently from queries that we had for sparse functions. All right, now we have our good notion of simplicity. I just have to tell you what are DNFs. DNFs are Boolean formulas that are made of ORs of ANDs. Or more precisely, it's an OR of ANDs of literals. So we have an OR on the outside, and each of those pieces are called terms, and they are ANDs of either a variable or its negation. Now, if we just leave it at that, then every Boolean function can actually be represented as a DNF. But this DNF might be very large and complicated. So in order to say something meaningful, we have to look at some parameters of that DNF. The most important parameter is the size of the DNF, which is just the number of terms. So in this case, we have 1, 2, 3, 4 terms. So the size is just 4. And another relevant parameter for this talk is the read of the DNF. And this is the maximum number of occurrences of a single variable within the formula. And for example, x3 occurs 3 times in the formula, and no variable occurs more times. So this means that the read of this DNF is 3. In general, for this talk, you can think of the size as being polynomial in n, the number of variables, whereas the read would be quite a bit smaller, for example, log n. And another remark is that the read is always at most the size, simply because a variable would never occur more than once in a term. Now that we know what simple means and we know what a DNF means, we can finally state the question that we're interested in studying in this paper. And this question was formulated by Mansour in a 1994 paper. And the question is, can every size S DNF, is every size F DNF 0.01 concentrated on poly-S coefficients? And I could have replaced this 0.01 by any small constant, is just to be a bit more concrete. So in our representation, in our visual representation, the question is, if you start with a size S DNF, can you split up the coefficient into two parts, one of which has area at most 0.01, and the other has only polynomial in S squares. Now, despite the fact that this is a very natural question to ask and about a very famous class of Boolean functions, the answer is not known. What is known before this paper is that they are concentrated on S to the log S coefficients. And what we show in this paper, on the other hand, is that they are concentrated on S to the log K coefficients. And as we saw on the previous slide, K is always at most S, so this is never worse, and this is better when K is not too big. And we also have another result which say that when K is pretty small as a function of S, then we get all the way down to poly S. So not just dot S to the log K. All right, so I will now give you slight taste of the techniques that were used in this previous result, and also then a slight taste of what we do to get the improved results. All right, so let's start with the previous results. And I like to call this the total length method, but I don't think anyone's used this term before. And the reason why will become apparent in a few moments. So the premise is that suppose that you have obtained an upper bound on the sum of the absolute values of the Fourier coefficients. Then I claim that you can get some result about the Fourier concentration as well. So yeah, to see why this is, we'll take our visual representation of the Fourier coefficients and put all of those squares side by side in decreasing order of magnitude. And we'll try to separate them into two groups so that one has few squares and the other has small area. To do that, we'll choose a threshold, h, such that we'll include all of the squares with side bigger than h in some part, and all of the squares with size smaller than h in the other part. Let's start with the part on the right. We want to bound the total area of this part, and we could do it simply because it's included in this rectangle. And this is a rectangle where the width is at most L and the height is h. So we know that the area here is at most L times h. On the other side, we know that each of those squares has a side of at least h, and the total length here is at most L. So that means that there's at most L over h squares. Now we just have to pick an appropriate value of h, and we can pick it to be 0.01 over L, which then gives us 0.01 concentration on 100 L squared coefficients. And since in general we would not care about polynomial blowups in this number of coefficients, this means that if we can prove some bound on the sum of the absolute values of the DNF of the Fourier coefficients, then we can prove a similar bound on the Fourier concentration. And then Mansour concluded in the same paper where he asked the question that the sum of the absolute values for a DNF of size S is at most S to the O of log S. This means that, as a direct consequence of the previous slide, that all size S DNFs are 0.01 concentrated on S to the O of log S coefficients. So this is great, and this is a beautiful technique. But the issue is that this S to the O of log S bound on the sum of the absolute values is actually tight, even for DNFs that are very simple, and for DNFs that we know are concentrated on fewer monomials than that. For example, the tribes function, if you've heard of it, it's a function where each variable appears only once in the formula. So it's kind of as simple as it gets. And we know for a fact that it's concentrated on poly of S coefficients. And yet, even for that function, this bound of S to the O log S is tight. So we have to have a new idea, find a new idea in order to improve this result. The new idea is term covers, which was suggested first by Lovett and Jagg. To explain what this means, I first need to take an alternate view of DNFs. We're going to see the terms of the DNF as sets of variables. So for example, T1 only queries variable x1, so we'll associate it with the set that contains just one. T2 queries variables x2 and x3, so we'll associate with the set 2, 3, and similarly for the other terms. So if we see DNFs in that way, that kind of associates to each DNF a family of sets, or like a family of subsets of 1 through n. And now I can tell you what a term cover is. So let's say that we're interested in figuring out an upper bound on the magnitude of some Fourier coefficient. What will be relevant here is if you look at S as a set of as a subset of 1 through n, and also each term as a subset of 1 through n, we'll be interested in ways to cover S with terms, or equivalently unions of terms that contain S. And we'll define a quantity associated with S, U of S, to be the minimum size of such a union. So the minimum size of a union of terms that includes this set S. And based on this definition, we can prove a bound on the absolute value of the Fourier coefficient at S. And the bound includes a factor which is exponentially small in this quantity U of S, and a factor which is an interesting combinatorial quantity, which is the number of ways that you can cover S in this with this minimum size. So the number of ways that you can cover S by a union of terms whose total size is U of S, so like the smallest size that it could possibly be. And I cannot tell you everything, all the details of how we use this ingredient, but this is the core ingredient of our proof. And shortly, the reason why it's cool is because it's both specialized for each S rather than being kind of the same for every S, which was the case for the previous techniques. It's also completely combinatorial, because once you apply this bound, then you only have to worry about the DNF as a family of set rather than as a Boolean function. All right, so I'm almost out of time, so I'll just recap on some open problems. The first one is the one that I've already mentioned, Mansur's conjecture, which conjectures that every size S DNF is concentrated on Pauli as coefficient. And even though in this paper we get some encouraging results for small read, this is still wide open for high read. And in fact, there's even one specific case that we have been unable to prove satisfies Mansur's conjecture, and this is Talleyrand's DNF. This is a randomized DNF construction where you take the OR of 2 to the square root n terms, each of which is an end of square root n variables, and each of the variables is chosen uniformly at random from the variables from x1 to xn. And the question here is still the same: is it concentrated on Pauli as coefficients, which in this case is 2 to the O of square root n. So if the answer is no, then this would disprove Mansur's conjecture, which would be a huge deal. But even if the answer is yes, I would consider that, if it's proved, then I would consider that great progress towards Mansur's conjecture, because it feels in a way like it is the hardest case, or like a key case that we haven't been able to prove yet. So I would be very happy to, if someone solved this, and I would happily buy you dinner if you answer this question either way. All right, so this is the part where I would normally ask questions, but since this is a recorded talk, I will invite you to put your questions in the comments, and I will do my best to get back to you with an answer. Thank you for watching.